So it is lecture number 3. Today's topic is conditional probability. In last 2 lecture, we defined what is probability, what is other different definition of probability, like classical definition or axiomatic definition, and different properties of the probabilities, different results, and then we discuss on the before probability we discuss on the sample space and random experiment, etc., events and other. Then we discuss on the independency of two event. What is independent? Now we start with independence. What is independent? The probability of A intersection B is equal to probability of A into probability of B. This is called independent. Now, what is conditional probability? Conditional probability is defined like that: A given B. This is called A given B, not A by B. It is A given B. Probability of A given B. So, probability of A given B. That A given B is the whole thing. This is a one word. It is not that probability of A given B. It is not like that. It is A given B is a one single word. It is not probability of A given something, not like that. Clear? So it is just A given B is a single word. So probability of A given B is probability of A intersection B. Or these are if A, B are independent. If A, B, independent. Divided by probability of B. Now, if probability of B is 0, then it is undefined. So we assume that provided probability of B is not equal to 0. If probability of B is 0, then A given B is not defined. If probability of then probability of A given B undefined. Now, clearly, so what the question is this actually is probability or not? That's the question. Basically, what is probability? Probability is actually what is first there is a random experiment and there is sample space omega, and there is a sigma algebra, we say, or sometime this is called sigma algebra on omega. What is sigma algebra? Sigma algebra means omega and phi must belongs to this sigma algebra. Then number 2 is if A in sigma algebra, then A complement. By the way, this sigma algebra is a subset of the power set of A complement also in this. So no need of writing this. You can just write omega belongs to, because then automatically phi belongs to sigma algebra because the complement is there. And number 3, if there is a countable collection of this set which are in sigma algebra, then their union, countable union, is called countable union. Sometimes write union I equal to 1 to infinity AI in this sigma algebra. So this is called sigma algebra. Now, in our case or in finite case, so if this is finite, we shall take the sigma algebra just a power set, just the power set. Now, this sigma algebra, this is called event space. We see saw it in the first class, event space, and any element of this event space. So any element A belongs to this. So A is called as event. So any event is just a element of event space, That means the sigma algebra, that means the element of the power set, that is A belongs to this power set. What is the meaning of that? That is same as saying that A is a subset of omega. Maybe empty, maybe a whole set. Now the converse may not be true. Any subset of omega may not be a event, right? Because we may take the sigma algebra is may not be equal to the whole power set. But if it is the sigma algebra, the event space is the whole power set, that means the power set is a collection of all subset. So collection of all subset is the event space. That means every subset is the event. And that may not be true. But in our case, if it finite, we will take any subset is event. But otherwise always true. Event must be a subset of it. So something like that. If we toss a coin, then this H, T is the sample space, and the event is events are pi, S, and set containing H. So H is not the event. We sometimes call H occur. Actually, H occur means actually the set containing H occur. Right? We can't talk about the probability of head. This is actually meaningless. The probability we actually say probability of head is half. The actual thing is the probability of set containing head is half. Just the set containing head is half. Because we have to find the probability of some events, that is a subset, not the element. We can't talk about the probability of an element. So head, tail are elements. These set are subsets are set containing head. So that notation must be the second bracket. Now, if I say this power set is the event space, that means any subset is event. Now, what is probability? Probability actually is a function, like function. Probability is a function from this sigma algebra or maybe the power set to the 0, 1. It's like a function. So, like a function, it's like a box. We take an input here. Input is actually event, which is a subset of omega, and we take an output, say probability of A. It belongs to 0, 1. Which is 0. This is from 0 to 1. Some definitions are there. But once I say this probability of A given B, what is the meaning of that? That's the problem. What is the meaning of probability of A given B? Then is this probability a function? Should I take input as A? Because A given B is not an event. This is not an event. This is meaningless basically. This is meaningless. This is meaningless. This is something meaningless. That probability of A given B is meaningful. So there is a definition of probability of A given B, but there is no definition of A given B. We can't say this is A given B. We can say what is A. We can say what is B. We can say hey, A means say set containing head is A, or head occurs, or head. Okay, rules is speaking head. Head means set containing head. Probability of head is probability of set containing head. So we can talk about A. We can talk about B. So or B maybe tail or set containing tail. But we can't say head given set containing head given set containing tail. This is meaningless, totally meaningless. Clear? So there is a meaning of A. This is a subset. There is a meaning of B. There is a meaning of probability of A, probability of B. There is a meaning of probability of A given B, but there is no meaning. This is meaningless, totally meaningless. Just A given B. A given B is not a set at all. Nothing actually is undefined. It's meaningless. So then question, then is this probability the same probability which are talking previous? No. This probability is not the probability of this. This is actually a different function. This is like a different function. Actually, it's take two input. This actually take two input. This P is different from the previous P. This function is not a function on sample space or not on the event space. It actually take two different input. Actually, it's take an input ordered pair input. And give the output probability of A intersection B by probability of B. Obviously, the such B we have to take that probability of B not equal to 0. We take that B, AB are now AB are set. AB is subset of omega. So remember, this probability P and this previous probability is different, totally different. So conditional probability and that unconditional thing, that simple probability, is not the same thing. So when I talking about the conditional probability, that means it takes two input, two different event we have to give, first and second. That's first probability of the first one given the second one. The meaning of this is probability of A intersection B divided by probability of B. So we have this so remember, this P and this P is different. These two are same. This and this, the numerator denominator P is the previous probability. They're that function. So that means you have to take two event or two subset of omega sample space. We put in this function on this box, give the output, this probability of A intersection B. How do you know the probability of A intersection B? That we have to form the previous P. That we take input A intersection B. If A and B are subset, then A intersection B is also subset. So it give output this. We take that output. Obviously, this P and this P are different because the input are different. That this the first P, the simple unconditional probability that can't take two different sets. It should take only one set. And this conditional probability, they can't take a single event. They have to you have to give two different events. So if you want to write a program on that probability to find the probability, you have to write two different programs for two different probabilities. So this is called conditional probability, and this is by definition. We write this. Actually, we can say this by notation. This is a notation for this. This actually the right hand side is better. We said this is a definition of probability of A given B is A intersection probability of A intersection by probability of B, but it is better to say that probability of A intersection by probability of B is by notation. We write this as probability of A given P of A given. Remember this again. This right hand side P is not same as the left hand side numerator and denominator. Numerator denominator are the same P, but in the right hand side the different P is called conditional probability. We use same for P. Actually, for if there are two different experiments, say, then must be two different functions, two different experiments, two different. So we toss a coin and we throw a die. Two different event space, two different sample space, must be two different function because the domain is different. The domain is the different event space, two different event. So we should write two different function, but we use the same P. Remember, we shall use all the same the notation P for the every probability. So, but you should be very cautious about that. The same P notation is everywhere, but this same P notation, but this meaning is not same. Meaning is not same. So meaning is not same. Okay. So this is called conditional probability. Say now, what is the independency through the conditional probability? Independency via conditional probability. That now it is very easy. So probability of A given B, if A and B are independent, then probability of A given B is just probability of A intersection B by probability of B. But probability of A intersection B is probability of A into probability of B. This is for independency. If A and B are not independent, we can't say this. Now this is probability of A. So if they are independent, the meaning is the probability of A given B is same as probability of A. So conditional probability, the probability of A given B is same as probability of A. So it is whatever is B is given or not, is conditional or unconditional, both the probability is same. That's why it's independent. We talk about independent. So there is a two definition of independence. Independent, we can define independent like that: A and B are independent if probability of A intersection B is probability of A into probability of B, or we can define probability of A given B is probability of A equal. So two different definitions. So one definition is probability of A give intersection B is probability of A into probability B. Now this all these three probabilities are the same probability, same function. Now the second definition is probability of A given B. Now this for P is not same. This is different. Is probability of A. Now this P is same as this. These three P's are same, and this probability is conditional. So this is different from the other three. Now these two are equivalent definition, because by definition of A condition A given B is say, but there is small thing. If probability of A given probability of B is 0, then what happens? If probability of B is 0, then this second definition is not valid. Still the left side is valid, because if probability of B is 0, then probability of A intersection B is 0. So it is clear that any subset must be probability 0. So if probability of A B is 0, then probability of A intersection B is 0. So that means left hand side is 0, right hand side is 0. So equality hold. So that means if probability of B is 0, then any set A and B must be independent. But this is by definition 1. But by definition 2 is undefined. By definition 2, we can't say the phi set. So phi and A may be any set, are independent. But independent by definition 1. So it is definition 1 and this is definition 2. But it is not, you can't say by definition 2 it is independent, because in that case A given phi is not defined. A given phi is not defined. So in that that's why the definition 1 is slightly better. It's not actually equivalent. It's slightly better because in one case, if one of them maybe is phi, then we can define independency, but we can't define by using definition 2. But we can define using definition 1. So this is a small advantage of definition 1 over definition 2. But still, definition 2 is slightly more easy to visualize, actually, more conceptually better, because so given something is same as not unconditional is same as conditional, that means like independent. So now given an example, it will be very clear. So one example is there. Now example is like that. Say we toss a coin twice. Toss a fair coin, say fair coin twice. So what is the sample space? So set containing HH, HT, TH, and TT. So HT and TH are different because they are fast head and then tail, then fast tail and then head. So since a fair coin, so is unbiased coin. So probability of all this in by the way, this is a single set, all this called elementary event. All these elementary events are with same probability, so all are same because they are fair. So we have no extra probability on over of one over the other. So all these four outcome or actually outcome is not, we can't say probability of outcome. Actually we have to say the probability of an elementary event. So outcome is actually the element, that HH. So the probability of we actually say by notation, we use this notation, probability of HH means it is actually probability of set containing HH. Strictly speaking, probability of HH is actually meaningless. We should say probability of set containing HH. Just okay, if I sometimes write probability of HH or probability of H, we assume that is actually the set containing HH, single element. HH is the single one outcome. HH is not the outcome. HH is the outcome because we toss a coin twice. Now these are all 1/4, right? 1/4 because all are equal chance, because this is a fair coin. Probability of head and probability of tail are same, or half of. Now say if I say the probability of head given, say, or we say probability of probability of head and tail head. That means the what is the meaning of that? This is the event where the second toss is head. First toss is anything, maybe head, maybe tail, but second toss is head. If I say if the second toss is head, you then what you can say what is actually event? If I say the second toss is head, that means it is a HH set containing HH and TH. Now, given that the first coin is toss is head, so it is HH and HT. So, what is the probability of this? Conditional probability. Now, this is intersection of these two. What is the intersection? Intersection is just HH and divided by the conditional part. Now, what is the probability of this? This is 1 by 4. And what is this probability? It is 1 by 2. So, it is just half. And which is same as the unconditional probability of HH and TH also half. So, the second coin is head is probability is half. The first coin is also probability half. The first coin and second coin both are head is 1 by 4. So that means if I say the conditional probability of the second coin is head, a second toss is head, given that the first toss is head, is just half. If you don't say anything, okay, what is the probability of the second coin is head? You will say it is half. If I say, okay, what is the probability of second coin is head, given that the first coin is head, again half. That means that the second coin is second toss is not second coin. The second toss is head and the first toss is head. These two events are independent. So that means the result, the outcome of head or tail in the second toss does not depend on the first. Doesn't depend on the first. What are the what about the maybe the outcome of the first toss? It may be head or maybe tail. It does not affect the probability of the second toss is head. So does not. So that's why the we sometimes call the not only for the head, it is also true for the tail. It is same as the second toss is tail is independent with the second toss, first toss is head. The second toss is tail is independent with the first toss is tail. So that's why you say the second toss, the outcome of the second toss, the probability of the outcome is actually the same as the conditional probability of the outcome. That same outcome given some first outcome. That means the first toss, result of the first toss and the result of the second toss, these two events are whatever this head or tail. There are 4 combinations. These are all independent. It's obviously, by it is a natural thing. So if I toss some coin, whatever it or mean, second time it does not depend on the first. Doesn't depend on the first. But if sometimes it may depends, then it is not independent. It is all dependent. So one idea is for the dependence. Now you say they're tossing another example. Tossing roll a die. Roll a dice. So there are 6 outcomes: 1, 2, 3, 4, 5, 6. Is yes. Now, if I say just one time, if I say the probability of the outcome is even, outcome is even. What is that? Even means just 2, 4, 6. So it is just out. Say it is 2, 4, 6. So it is 3 by 6. Oh yeah, that is a fair die. It is a unbiased die. Unbiased die. Something called fair die, unbiased die, uniform die. So it is everything is 1 by 6, 1 by 6, 1 by 6, 1 by 6. So 3 by 6 divided by it is just 3 by 6. Half. If I say probability of say 1 to 3, what is this? Again, it's 3 by 4, 6 half. Now, if I say what is the probability of 1 to 3, given that it is even 1 to 3, given that it is even. Outcome is even actually. Outcome. Now this is just in numerator probability of the intersection, only 2, and it is outcome is even, divided by outcome is even. Now what is this? Is 1/6 divided by half, so it is 1/3. So not same as the unconditional probability. So it is obvious thing, because it is in the same toss. If I say the outcome is even, that means the probability of 2 is slightly less, because it is among the 2, 4, 6. If I say outcome is odd, given that outcome is odd, then it is 3, 2/3. Then that means, what is the meaning of this? What is actually the concept of conditional probability? That means, say, if I ask you, say, I roll a die and I know the result. I know the result. So for me, if someone asks what is the probability that already it's one occur, I know the probability actually, because I know the result. So result is a 4. I know the result. So I will say it is just 0, because I know that it is 4. If someone asks me what is the probability that this die outcome is 4, I will say it is 1, because I know the result. But if, say, you don't know the result, someone asks you, okay, sir, rolls a die and sir know the result, but can you say what is the probability of this outcome is 2? You will say it is 1/6, because you have no information on that. So if you have, I have the all information, so I know what are the probability of 4 and what is the probability of 1. So it is only 0 and 1 to me. If I know everything, the probability will be 0, either 0 or 1. But you don't know. But you know that the probability is one of the outcome is one of the 1 and 1, 2, 3, 4, 5, 6. If someone asks you what is the probability that the outcome is 7, you can say it is 0. 7 can't occur. That you know. But you don't know what is occurred among 1, 2, 3, 4, 5, 6. So you will say it is just okay. It's a fair die. Say okay, it is a fair die. It's every probability is same. All the 6 probabilities are same. Then it is 1/6. But if someone, you say your friend, that he knows that the outcome, somehow he knows that the outcome is even. You know that the extra information. You don't know whether it is 2, 4, or 6, but you know the fellow know that it's even. I give some information. Okay, I'll say it is even. Now this is the idea of the given thing, given conditional thing, and that fellow, that your friend, has an extra idea, and that he can. Now, if I someone asks him that what is the probability of 2, or what is the probability of 1 to 3, or what is the probability of 2, then what is the probability of 2 then? What is the probability of 2? Sorry, what is the probability of 2? 2 means it is just set contained 2. Given that is even, right, short in short. So it is just 1/6 divided by 1/2. So it is 1. Oh, sorry, it is yes, it's right. 1/3. So probability of 2 is now 1/3. What is the probability of 4? It is again 1/3. What is the probability of 6? 1/3. What is the probability of 1? That is obviously 0, because you know the outcome is even. What is the probability of 3? It is again 0. What is the probability of 5? Is 0. So actually you go very close. Now you are going closer to the actual thing. So they say actual outcome is a 4. So there are 3 persons. 3 persons are there, say. I know the result, so I know the corresponding probability. Say 1, 2, 3, 4, 5, 6. I know actually the where 0 and where 1 is. I know this is 1. These are all 0. These are the probability. That fellow, if you don't know anything, unconditional. And there is no everything actually. There is nothing unknown. That is 1/6, 1/6, 1/6, 1/6, 1/6. Now, if someone knows it is even, that the outcome is even. then it is 0, 0, 0, 1 by 3, 1 by 3. If I give one extra more information, okay, it is even or and greater than equal to greater than or equal to 3, then it will be half, because only 4 and 6 is left. If this extra information actually if affects the probability of the actual thing, is actually it is 1 is here, and no information is just 1 by 6. Some information is given to the 1/3, so close to 1 by 6. 1/3, 1 by 6 is 0, and it is a 1. It is actually it is 1, but if you no information is 1 by 6, change to 1/3. That means this is not independent. That probability of 4, given that is even, the probability of 4 and the outcome is even. These two are not independent actually, because it changed the conditional probability. This information actually gives actually have give some information. If I say okay, it is now if it's even as well as greater than or equal to 3, then this probability will be half the conditional probability among 4 and 6 only. Again, it's a one extra information. But if I say okay, what is the probability of if I ask you that whether the second toss is head or tail, you have no idea. You'll say half. You say okay, I give a information. The first toss is head. Actually, this information is no help actually. After this, given this information, again this second toss is head, and head or tail is half. Probability of head is half, probability of tail is half. So that information, the first toss is head, actually does not affect the. This information doesn't affect the actual probability, whatever the conditional or unconditional. That's why the conditional thing. So independency through conditional by probability is conceptually better, but algebraically, this probability of A intersection B is probability of A into probability of B is algebraically better. Through some calculation purpose, it is better. But actually, by motivation or by conceptually, this is actually no meaning. What is a condition? What is the probability of A into probability of B? There is actually no interpretation of probability of A into probability of B. Okay, probability of A, I know what is probability. I know what is probability of B. I know what is the intersection. But probability of A into probability of B is actually no interpretation. How do you interpret this? Product of probability. But here, conditional probability you can interpret in terms of that ratio you can interpret. So that means probability is changing now. So the information, if they are not independent, will rearrange your all the probabilities. If I ask you what is the probability that some team in T20, say unknown team, some Buena or some other teams are there now in the first round. If I say what is the probability that this team will be win over the other team, you will say okay, I have no information, but this is not a good team. Okay, it may be 1 by 10. But if I say no, this team is already they beat Bangladesh or something like that. Oh no, then this probability 1 by 4. This information actually is not independent with that outcome. So outcome is also a event, is a subset. Outcome, sorry, the event is a subset, and the given thing, that given information is also a subset. And these two subsets are independent if algebraically the intersection, probability of the intersection is the product of the probability, or by conditional probability, it is just A given B is equal to probability of A. Now there is some result on this, very important result. Say if probability of A given B is probability of A, then we can easily set that probability of A complement given B is also probability of A. And we can say that probability of B given A is same as probability of B. And you can say probability of B complement is given A is also probability of B complement. Also, you can say that probability of A given B complement is probability of A, and probability of A given A complement given B complement is also probability of A complement, and probability of B given A complement is probability of B, and probability of B complement is just a homework to you. Actually, if I say one of this, you can prove the other 7. So these all are equivalent. If I say one of them, you can prove the other 7. If I say okay, I say it is 4 is hold. From 4 you can easily prove 5, 6, 7, 8, 1, 2, 3. Anyone. So that means there are actually 7 into 8, 56 different type of problem. 56 many problems. If I say okay, I give you 7, prove that 2. Okay, assuming 6, prove 4. So there are 56 many such a question will be there. No need of solve all these things. You just if you if you just say if you prove 1 implies 7 or 6 implies 3, you have an idea how to prove all these 56 result. These are very easy. So it is left in the homework. So these are equivalent. All these are equivalent. Prove that the following are equivalent. The following are equivalent. Now this is a very important idea of independency. And this is by conditional probability. Now conditional probability has different use. So I have one more example. I will give one more example on conditional probability. These are more textbook actually type example. Say there are 3 drawers or 3 boxes. There are 3 boxes. Each box contains a different type of say red and blue balls. So sometimes of red and blue balls. So say 4 red and say 6 blue. Here say it is say 5 red and 5 blue. Say it is say 7 blue and 3 red. Maybe may not be all the 10. Maybe okay, it is 7 red and 5 7 blue and 5 red. Now I toss I roll a die. If 1 or 2 occur, I choose this first box. If 3 and 4 occur, I choose the second one. If 5 and 6 occur, I choose the third one. So I roll a die. I know what is the outcome of this die. Accordingly, I choose the box. Then I took a ball from that, only one, or randomly, without seeing this. And what is the probability of this ball is red? Now, this is actually conditional probability. So there are actually 3 events are there. So A1 means this first box is choose A2 and A3. So probability of A1 is same. Is A1, A2, all are same. All are 1/3. Okay, it is a fair die. Now, what is the probability that say red occur? Red means say R means red. R means red ball or R means red ball occur. That means set containing red. Given that A1, what is the meaning of that? It is given that the box is A1. So if box is A1, the other box has no existence of the other 2 boxes. So it is just 4/10. Because there are 4 red balls, randomly you are choosing from the 10. 4C1 to and 10C1 divided by 10C1. What is the probability of red given A2 from the A2 ball? It's just half, 5/10. Now what is red given A3? It is just 5/12. Similarly, the blue given A1. Now, what is the probability that this red occur? Now, to find this value, you have to actually draw the Venn diagram. So this is the whole set S. This is the A1. This part is A1. This is A2. This is A3. And so this is red. Now this part is A1 intersection R. So this is actually the R intersection A1, the first part, union this part R intersection A2, union this last part R intersection A3. Right? Now these are all disjoint because A1, A2, A3 are disjoint. Remember this A1, A2, A3 is done. So if you choose one box 1, you can't choose box 2. You have to choose only one box. Actually, if you could toss if you roll a die, the only one, it can't occur 2, 3 at a time. It's just one time we throw a die. Now this is so it is just a add the sum of this. We know if it's in disjoint, we just add this. It is clear from the picture. The 3 different event. If we add all this probability, you will get the whole probability, right? Because something like that, if I probability, if I draw 3 lottery ticket, we buy 3 lottery ticket. The first lottery ticket has a probability, say winning the first prize is say 1/10. The second one is say 2/10. The third one is say 1/10. To win the winning probability for me for any of the one of the 3, only one first prize is there. One of the 3 ticket is just the sum of all this. So now you have to use a conditional probability. What is a conditional probability? It is just R given A1 into probability of A1 is by definition. By definition, R intersection A1 probability is this. Remember, all these P notations are not same. This now next conditional P is different, but we are using the same thing. Otherwise, there will be everything will be very mess. If I use different notation for different thing, but you have to very careful about this. Sometimes we use the same notation for different purpose, like a same name for the different students or different persons, a same word for the different meaning. There's in English or in Bengali, there is same word for the different meaning, something like that. But you have to be very careful about this. And what is the meaning of this? You can actually get from the context, basically from the text, from the full line. Individual that word you can't say what is the meaning of this word, because this word has say 10 meanings different. In English, say that, so in Bengali some word has say 4 different meanings. If I ask what is the meaning of this word, you have to say, okay, I can't form just what I can say this. You have to know the whole the sentence. Then I can say what is the actual meaning of this word in this sentence. So similarly for the P, this P, once I get the P, what is the definition of P? What is the meaning of P? You can't say actually. The P, you have to know what is the P of unconditional or conditional P is a function from where to where. These all things you have to know. If you don't something is there in problem, you have to ask what is the actual meaning of this. Now we know all this probability. We know this. It is just half, 1/3 plus 5/12. So this is the probability of red. And what is the probability of blue? This is a 1 minus that. So by using conditional probability, you can find the probability of this. This is called marginal. Sometimes it's called marginal. Actually, there are 2 different array there. 2 different one. The whole scenario is actually break into two different two way actually. The whole S actually break into 2 ways. One way it is just red or blue, and other way it is just A1, A2, A3. The first box, second box, third box, something like that. And this is called, it is a whole sample space. In break in this way also, in this way also. So A1 union A2 union A3 is again S. Also R union B is also S. R means the red ball occur. A1 means the first box. We choose the first. That is 1 and 2, 1 or 2 occur. One of them occur. One or between 1 and 2 for the throw right. Now this is called, or sometimes called total. Is not total. It's called marginal. Sometimes called marginal. In probability language is actually total. Now we know that this total is just 1/3, 1/3, 1/3. All over is 1/3. You can find this using this conditional probability. And this here it is in intersection, probability of A1 intersection R, this probability of A2 intersection R, this probability of A3 intersection R, this probability of A1 intersection B, probability of A2 intersection B, and probability of A3 intersection. Now this is probability of R actually, and this is sum is probability of B, blue one. Obviously sum of the R and probability of B is 1, summation. This is one third probability of A1, probability of A2, probability of A3. How do you find this conditional intersection? Use the conditional thing. We know the conditional probability. We know this. Ri given Aj. We know this all this result, and this is actually probability of Ri intersection Aj divided by Aj, probability of Aj. Now I from 1, Ri means it is it is R just. J from 1 to 3. Similarly for probability of blue given Aj. Same. Now using this, you can find the intersection part, and then you can easily find this marginal. Now there is a tree notation for this, branching notation. So this is S, the total probability is 1. Now you have 3 branch, sorry. Each branch, 3 branch means in the first step experiment, it is just A1, A2, A3. The probabilities are 1/3, 1/3, whole probability divided by 3 different branch, 3 different root. Now again there is a 2 different root, is A1 intersection R, A1 intersection B. Now we know what is this here. What is the conditional probability of this? What? 4 by 12, 4 by 10. So it is just 4 by 10. It is 6 by 10. So it is a part. So it is not actually, this probability is not 4 by 10. It is 4 by 10 into 1/3. This here probability is 4 by 10 into 1/3. So it is 4 by 30. So this is a 4:6 ratio. Similarly for the other thing, A2 intersection R, and here A3 intersection R. Now you can just collect all these things. You'll get R. And if you collect the other 3, you'll get B. And if you collect all this, again yes. Now this probability are given to you actually on this sided, the left sided. This is something called prior probability, and this is called posterior. This prior thing are given because the experiment is such a way that the ball is not the first. The box choice of box is first, then choice of ball. So the next step is ball. There is a hierarchy. Now, if I ask you the other way, say what is the probability of A1 given that is R? That means I told you that it is okay. This ball is red. Okay, it's given that there is information. Box is ball is red. What is the probability that it actually came from the box 1? You don't know. I know. Say, if someone don't know anything, if I ask you what is the probability the ball came from, if I don't say any color, if you ask me what is the color, I don't know any color. Then what is the probability of choice of the box 1? It is just 1/3. You have no information. It's just 1/3. If I know from where box it is, for me it is just 1 or 0. But if I say, okay, the ball is red, now this probability is not 1/3. If I say that, okay, the last thing, the last outcome, the ball is red, can you say from which box it came? What is the probability for each box? Now what is this? This is just probability of A1 intersection R divided by probability of R. Great. But we know the probability of A1 intersection R. What is the probability of A1 intersection R? We calculate this. It is just 4 by 10 into 1/3. It is just 4 by 10 into 1/3. Now what is this? This is the sum of all 3. If you take 1 by 3 common, so 4 by 10, half, and 5 by 15. If you take 4 by 10, half, and 5 by 15, 12 into 1/3. What is this? This is 4 by 10 divided by, say, it is what? It's 60. It is 24, 30, then 25, 24, 30 and 25, so it is 79. So 24 by 79. So it is not one third. It is not one third. It's slightly less than one third. The conditional probability is now reduced. Why? It is very easy from the idea, from this problem, because the first box contain less number of red ball, while the second box contain the much more ratio. It's 50-50. It's 5-5 and 4-6. That means the red, since it is came from the red, since the red ball is the probability from the second box will be high than box one, because if I say one box say contain among the 10 balls 1 red balls and 9 blue balls, second box contain 10 blue balls, say, and third box contains say 5 red and 5 blue. If I say the what is the probability of it is coming from the second box, given that is red, you can say it is 0 just, because in the second box there is no red ball. If I don't say anything, if I say what is the second box is occur, what is the probability of second ball is occur, you will say it is just, you say it is just one third, because you don't know anything. If I say that okay, if extra information that the ball is red, then okay, then its probability of the second box is 0, and is probability of first box and third box should not be half of, because from the coming from the red ball coming from the first box is much less, because if it is the first box is already chosen, then coming red ball is very low probability. It's just 9 blue, black, blue, or 9 blue and 1 red. Whether the third box it is 5-5. So that means it is actually coming from third box is very high probability. So now it is not one third, one third, one third. So that's the idea of conditional probability. So the information actually what is given to you is actually affect the probability. If you don't affect the probability, then it is independent. But these are not independent. This draw of red ball, drawing blue ball with the box A1 into A3. The three A1 into A3, this A1 and the red, this is not independent. These are dependent because the probability is changing. So this, and now you can find this is by a very good method, which is called the tree method. But in textbook, this method is not actually allowed. But in MCQ or in different exam or in your satisfaction, you can use this tricky method, something like that. Uh, say you are repeat this experiment say 60 times. If you repeat this experiment 60 times, what happened? If you repeat this experiment 60 times, what happened? On an average, 30 times, if you repeat this experiment 60 times, on an average 20, 20, 20 of the each box, actually it's one third, one third, one third. One break into one third. Actually, this multiplied with 60. Same thing. Now for first box, the number of red ball, the number of times the red ball will be just 8. For this is 20, so it is 10. Now it is 12. Oh, how it is 12, no? So how it is come 60? It should be 120. Otherwise, no, you can take that, but it will be a fraction. So take 120. 120 better. So 40, 40, 40. This 16. This 20 times red ball occur. Now for here it is 60. Sorry. What? How it is not no 60? It should be 180. Sorry. Is it need 180? It's a 12, one third. What is the LCM for that? Is my calculation is correct? LCM the correct calculation. Oh, actually the 1/3 is just cancelled out. That's why it is 60. Oh, 1/3 is cancelled out. That's why it is 60. I take 180. Right. Because it is same 1/3, 1/3, 1/3. Otherwise, so 60, 60, 60, 60. Red will be, how many red will be there? Red will be so 24, right? Here it is 30. Here it is 5 after 12, so 25. The total red is total number of red occur on an expectation. Actually, it may not be true. Maybe if I do this experiment 120 times, it may so happen 110 times red occur. But on an expectation, we expect this 24, 20, 30, and 25. That means it is what 79, and out of this 79, the first it is coming from the first box is 20. So this actually same as this probability, this calculation, same thing, but only advantage is you are doing with integer because you are multiplied by the LCM. No need of this type of fraction thing. Actually, it is same if we just multiply by 180 both numerator and denominator, you give the same thing. So, but this method is allowed, but that taking 180 times, that is not allowed in written test, but you can use in MCQ test or your own check. You can do this because otherwise that summation of some adding some fractions, then multiply with some fraction, maybe some error, mistake. But if it's all the integers and then add integers, then it will be easy. So this is a probability, and using this you can easily find the actually this tree is actually you can find any probability using this tree, conditional or unconditional. If I ask you, say, what is the probability of red given A2, it is just 30 by 60. It is 30 red, 30 by 60. If I say what is the probability of A2 given red, then you have to count all this 8 red, 30 divided by all these 3, sum of all these 3, because these are the total number of red, and out of this total number 30 came from A2. So probability of A2 given R means it is probability of A2 intersection R divided by probability of R. Actually probability of R means it is just actually every time it is 30 by 180, 30 by 180, 60 by 180, 24 by 180. That is one by 180 is always there, but it is actually cancelled. So we have this idea. So this is called posterior probability. So how do you find this posterior probability? It is easy. So finding some probability AI given R, you can write this in terms of probability of R given AI is actually probability of R intersection AI, which is probability of R given AI into probability of AI. This is actually probability of R intersection AI divided by probability of R. Probability of R means it is probability of, again, R intersection A1, R intersection A2, probability of R intersection A3, which is probability of R given A1 plus it is I, probability of R given, probability of AI is there into probability of AI, A1, probability of R given A2 into probability of A2 plus probability of R given A3 into probability of A3. So you can write this. The other condition is called posterior. That is not clear from the experiment. This probabilities are clear from the experiment. This R given AI. If the first box is there, then it is clear what is the probability of red. But if the ball is there, what is the probability of boxes? First, the box is the first box. That is not clear. That you have to find using this result, using this formula. This is very important formula, and this is not only for the 3 case. Maybe so happen there are, say, 10 many box. There are 10 many boxes, and that red and blue. Maybe red, blue, and green. Maybe red, blue, and green. So maybe the tree may be something like that. In first time it is just 6 branches, and every there is a 3 branch. then that all the conditional property you know, this A1, A2, and this has say B1, B2. We know what is the probability of A1, A2, A3, probability of A1, probability of A2, probability of A3, probability of A6. We know probability of B1 given A1. We know probability of B2 given A1. We know probability of B3 given A1. We know probability of B1 given A2. Probability of B1. Now I B1 given B1. To use this result, this idea, and the proof is clear from this previous example. And this is a very important result. This is due to Bayes, and this is called Bayes theorem. It's called Bayes theorem. Bayes theorem. Actually, this is a Bayes theorem. What Bayes theorem says? Bayes theorem says is A1, A2, AN dot 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 dot. N are one thing. A1, A2, A3 must be mutually exclusive. Must be disjoint. Mutually exclusive means may not be independent. Here, there is no question of independent. Mutually may be independent. If it is independent, then it is easy. Mutually, in the previous example is not independent. Mutually exclusive. What is the meaning of mutually exclusive? It is disjoint, pairwise disjoint, something called pairwise disjoint. So if mutually exclusive and there is even B, another, it not from the A1 to A. B is different, and we know all these probabilities. So B given A1, AI is we know. So we know this probability. This is a known. Now, how do you find AI given B? To find probability of AI given B, it is just probability of AI intersection B divided by probability of B. But how do you find probability of AI given B? AI intersection B. This is again using that conditional probability of B given AI that we know. These are also known. Probability of AI also known. These are all known probability into probability of AI. And how do you find this B? This actually B is nothing but the union of this B intersection A1 union B intersection A2, because by the way, this is not only mutually exclusive and exhaustive. Sorry, exhaustive. This is disjoint, and that union is, that means exhaustive means that union must be the whole set. This A1 into A3 must be the whole set. And in mathematical language, this, if they are mutually exclusive, disjoint, and the whole set, this is called partition. It's called partition. It's called the partition of this whole set. A1, this is A1, this is called partition. In mathematical language, we know this is called say partition. A4 and A5, A6. And we have another set B, say something like that. Now, once this AI is partition S, that means AI intersection B, that partition B actually. That makes the partition of B. Because the B1, B intersection A1, B intersection A2, they are all disjoint. And also the union must be B. So that means it is a, if you take the probability, this will be a sum of the all B intersection AI, I from 1 to n. Now we know what is the probability of B intersection AI. It is just probability of B given AI into probability of AI. So this is called the Bayes theorem, renowned Bayes theorem in probability. Very important theorem, but very intuitive. It is easy and clear. Actually, very simple, straightforward, but very, very useful. And actually, in probability, the most useful theorem in probability, the Bayes theorem. So today, a conditional probability and all these things up to this.